Now we come on to a big class of, and actually reasonably, which of environmental, earth, and planet science. These are all connected because they're studying the real world. So they're sort of situated in three space and one time dimensions, which is not so clear you're doing that for particle physics, which are quantum physics, and therefore not, they aren't really geolocation. Everything doesn't matter for particle physics. So we start off with IceCat, which is a um, facility being built in the Nordic regions, and it's basically scattering radar in the atmosphere, measuring what happens, and using that to investigate the dynamics and structure of the atmosphere. And currently it operates the so-called 10 radar scattering instruments, and it takes data which is then recorded and sent back to the central facility for analysis. The current version is very small, terabytes per year, and there's no real special challenge. It's not a big data application. But the next generation is going to be 5 sites, 40 petabytes of data per year, and it's going to run like this maybe for 30 years. So this is going to require really significant high performance computing, and also going to require multiple sites to be integrated together. And this is not a real-time effect. It's can be done in batch mode, and except the real time is obviously needed to monitor the quality of the data and the operation of the instruments. This next slide here gives the so-called architecture of what's going on here. And we have the mirror sites up here. We have the high-performance computer. And the high-performance computer is here, long-term storage, mirror site. And here we have the receiver, specialized analysis, runs through the preprocessors, and then it basically goes to storage, and that's when it comes transmitted to the offsite facility. This is on-site, this is off-site. Whenever you have instruments or sensors, it's very important to decide what processing is done on-site and what processing off-site. We saw that with the military sensors because you needed, you had this problem, you need a lot of processing, but if that processing is in some hostile environment, that may not be a very sensible place to put it. But if you transmit everything a long way, then this big data from a modern sensor is very difficult to transmit long distances. Here is a reasonably interesting case, HONVRI, which is a European project. And it's basically the idea is there are many projects in the environmental area, and they need to be try to reuse ideas between the infrastructures that support them. So this is a collaboration between multiple different environmentally related instruments, including the IceCat, the one we just did. And it's developed a reference model, which has got the ontologies for the metadata and the standards for specifying what's going on. And then it then is then applied into these 6 closely coupled projects and 2 loosely coupled projects, which are given on the next slide. And the idea, of course, is to promote reuse of the not unnecessary duplication of effort in the infrastructure. So there's 6 projects. We should go through these projects to show what they do. There is a distributive infrastructure, which is monitoring greenhouse gases through atmosphere, ecosystem, and ocean network of sensors. Argo is a global ocean observatory system, which is global but has a European component. IceCat we just did is the largest of these systems. LifeWatch we actually did earlier. EPAS is an earthquake, volcano, and surface dynamics tectonics observatory. And EMSO is a seafloor observatories inside under the ocean for long-term monitoring connected to the ocean ecosystems, which feeds into climate change and other types of studies. And then it has links to two other projects, CEOS, the Arctic Earth Observing System, and IAGOS, which is Aircraft for Global Observing Systems. So these are all a mixture of environmental and earth science projects, which, well, I guess even polar science if you do the Arctic Earth, which are linked together by the desire to maximize reuse of infrastructure and ideas and metadata and things like that. Here's a very generic architecture. You can see it's pretty generic. It's even more generic than the NIST architecture. We have community support. Then we have data processing, data creation, data acquisition, and data access. So these are some critical components. And so that's reasonably uncontroversial, I would think. And then we have actually for each of the subsystems and the picture of their particular architecture, which are not necessarily drawn in the same way. Like here we have ICAS, which has the different observers, ecosystem stations, atmosphere stations, ocean ships. Then these get fed into centers for each of those areas, a central analysis and coordination office. So this is really not a system architecture, but a project architecture, how the different components are linked together. LifeWatch, we discussed earlier, Project 25, and again, this is a pretty generic type discussion about how the processing and the community and the curation are linked together. Here's EMSO, which has these seafloor observatories. And again, this is a project diagram showing how the different activities are coordinated with a data center for various processes, local centers, observatories, autonomous instruments giving time series, and linkage to other projects with, again, community. And here we have, again, these same categories which were identified by OMVRI as the critical categories of infrastructure. Now we come to EuroArgo, which is the European version of the Argo Global Ocean Observatory System. Notice how we have the OMVRI categories: data access, community support, data processing, more on community support, data acquisition, data creation. So here with the data, here previously the data was at the bottom, now it's at the side, it's coming in through here, and it's got a lot of community and resources doing the different types of conversion that's necessary. So that's the end of OMVRI, and we now move on to the, ISCAT is the other infrastructure in OMVRI, but we already did this architecture, so we don't repeat it here. Now we have an application which we actually have some details of that later on in this course. So we have this is CRESIS, a project led by Kansas for remote sensing of ice sheets, and the information gotten by this project is actually very important in feeding into the work on climate change, because an aspect of climate change is what happens due to the Arctic and Antarctic. Recently, actually, in the news, there's been lots of discussion of various funny things happening about ships getting caught in the ice and things like that. And so whether climate change sometimes makes things colder and sometimes makes things colder in the winter and hotter in the summer, I don't know. Anyway, we're just, this is an uncontroversial science project, which is trying to quantify what we know about Arctic and Antarctic glaciers by and ice sheets by measuring their details. And this radar is able to penetrate into the ice and measure, for instance, the bed. It can also penetrate through snow layers to find the annual changes in snow from the layers you get at each year. It's interesting that this application is dominantly MATLAB based, like many engineering signal processing problems are. It involves radar images produced, which because that in remote regions you can't use the internet to transmit, you typically write them to disk and ship the disk back. And there's lots, and these disks actually don't last very long because they get pretty roughly treated due to the harsh environment. And we keep on having to replace these disks. These ice sheet bed depths are analyzed by image processing, which we'll discuss later on. It's all the data is taken in trips, which might take a few weeks in length, and gather 50 to 100 terabytes of data. Future data will be order of magnitude more, and other issues that are involved here are low power, because you would like you always have a power budget in these remote regions, so use of GPU systems is important. You also tend to use GIS here, Geographic Information System, to display the data which has been taken. Here's a typical example of glacier bed with lots of confusing additional signals. Here's the real seabed at the bottom here, 3,100 meters, sorry, glacier bed. And here's the aircraft taking the radar 500 meters above. In this particular case, the goal is to identify this bed. This is another GIS taken from this experiment, showing how the different aircraft flights are shown here in blue or red, depending on whether it's a DC-8 or a Twin Otter, because they use multiple aircraft. And then they look in detail from this GIS view as to which shows what the tracking of the aircraft, and then you can look at the data and find out. Click on these various flight paths and find out the data and look at its quality and so on. Here's a typical example of actually clean data with some automatic method used to identify the green as the top, and the red is the actual bed. Yes, it is pretty non-trivial. It is not constant depth. So this is air ice, and here's ice medium rocks.